All right, so today I'm going to talk about the inverse distance problem. And actually, surprisingly contrary to what we have covered so far in differential geometry, this one is actually more about the topics that we are familiar with, such as linear algebra and optimization. As you can see, there are like roughly two parts of this presentation. The first, the text in gray, they are from the MIT lectures, mainly from the lecture notes and the slides. I've also added some new materials after because I feel like it is a unity of like all the topics that we're going to cover. And in the end, I'm going to try to relate what we learn in this section to research. So to start, what is the inverse problem? In the previous lectures, we are given a manifold and we are computing properties of the manifold and define geometric quantities on the manifold. Now, the inverse problem is that we're given a matrix of distances and we are trying to recover the manifold, or in other words, embedding. So naturally, we shift our focus from manifold to metric space. So to start with the presentation, we need to first equip us with the necessary mathematical definitions. So the first definition is metric space, which I think we are quite familiar with. It's basically another way to talk about distance. And so intuitively, a distance need to be positive, need to be symmetric, and need to follow this triangle inequality. And this is the property that's used most in proofs. An example is a manifold that's equipped with the geodesics. This is a metric space. Another one is a Euclidean space equipped with the p-norm. The motivation under studying metric space could be because distance is a very natural way to encode similarities between objects. And the whole theory of metric space is very well studied. So if you use this model, you can use a lot of theorems at your disposal.
If you give geodesic as the metric definition, does it really satisfy the triangular inequality? I don't think so.
Okay, that's an interesting remark. Could you give example?
Example. So when the sum, what is the triangular inequality? Sum is larger than equal to.
So it's basically saying that for arbitrary 3 points in your domain, the distance between the first one and the third one is less than the distance between the first and second and the second and third. That's or equal to.
Oh, so here you are not thinking about any general manifold. Here you are just focusing on the sphere, S2.
It could be thinking about any Riemannian manifold, I would say.
Any Riemannian, that I doubt it. S2, let's see. S2, can we?
I think there's actually a theorem about it. It's all right. Could I maybe write an email later on, because I remember there's a theorem, but I cannot recall it.
Later. But this one general manifold, I'm pretty sure it doesn't hold. But yeah, I might be wrong.
Okay. All right. Cool. Let me just do some more research afterwards. Yeah. Okay. Thank you. So. Okay, so the second definition is embedding. In this case, it is applied to metric space. So you can see the mathematical.
By the way, yeah. If we somehow do not define the distance over the global pair of the points, but if we just limit our distance to the local neighborhood, then things are fine.
Yeah. Okay.
And that is really the definition of the Riemannian manifold, you know.
Yeah, the Riemannian matrix is equipped the tangent space equipped with, or the tangent bundle rather, equipped with a Riemannian matrix is a metric space. Yeah.
Right,
That one,
right.
I think, is well established.
Right. So locally we can define the metric, right? So that is not a
Yes.
problem. It's just that once you extend it to the global pair of the points, that I don't think, if I remember it correctly, I don't think triangular inequality holds there.
Sure. Yeah, that's an interesting remark. So yeah, I'm going to provide more materials after regarding this point. Yeah, thank you. Okay, so embedding in this context is just a mapping between two metric space. It's very general definition, but it's between two metric space. It's kind of less general than the embedding we see in machine learning. And isometry here is just saying that if the embedding preserves distance or the metrics between two metric spaces, then it's called isometry. And just want to give some definition of embedding in general in machine learning. When we talk about embedding, normally we don't just confine ourselves to a metric space. We say that embedding is basically what's learned from an encoder model to a latent space, where we expect that the latent space have some semantic similarity, between the inputs that can be mapped in into some structure of the latent space. It's a more general notion of embedding, and it's not confined to a metric space. So in the later presentations, I will reason about the relationship between the embedding defined with the metric embedding and this general sense of embedding. So to give an example of isometric embedding, here we have embed a equilateral triangle with edge length 1 into R2. It's very natural way, because when we think about a geometric shape, we actually have this intuitive notion that it's somewhere in the Euclidean space. But is Euclidean space like all powerful? Can you embed any metric space into Euclidean space? The answer is no. And this is a very rather simple counterexample. If you define a finite metric space of 4 points with the distances defined on the right-hand side, you can check the definition of a metric space that this one actually holds. It follows all the properties of metric space. However, it's not actually embeddable in Rn, because here, the first line is basically saying it's a equilateral triangle. Second one is basically saying that you have a midpoint, and the third one is connecting this one to the midpoint. And by just the basic geometry, we know this one is not 1.5, but this is a valid metric space. So in short, Euclidean space is not cannot embed even all the finite metric spaces. Isometric embedding, of course. So this is a proposition from the node, which is saying that the Euclidean space equipped with the infinity norm, which is the max element of the vector, this is actually a space that you can safely isometrically embed any metric space. So it serves as a toy example because it doesn't really serve any practical purposes, because you can't really do any sensible algebra in the infinity norm space. So I just want to bring about this proof. And if you're interested, you can take a look at the lecture note. Basically, it's not very related to everything else. And so instead of doing exact isometric embedding, normally we cannot do isometric embedding. So we need to have some measure of how good the embedding is with respect to the isometry. So this is notion of distortion. So the first one, expansion, basically you can see after embedding, it's basically the new distance over the original distance. So if for embedding expanding your original space, then this is greater than 1. Contraction, on the other hand, is basically how you squeeze or compress the original space. Distortion is the product of these two. And if a distortion equals 1, that means you have isometry. And this, as we know in machine learning, normally we can have an objective, and we can try to either optimize it or like maximize it or minimize it or confine it. So here you can easily devise a objective function such as distortion -1 as your optimization objective. And this actually, as I will later show, it's a blueprint for dimensionality reduction and manifold learning task. So just before we go into the details of the algorithm, here are two well-known mathematical results that's worth mentioning about. So this first one regards how good can we generally embed into a Euclidean space equipped with a p-norm. So this is called the Bergens Theorem. It's basically saying that if you have a finite metric space of endpoints, you can embed them into Euclidean space of O of log n squared dimension with a distortion of log n. So it's basically not too bad because it's in a log scale. So and the algorithm and this theorem is proved using a construct called a Fréchet embedding and other probabilistic techniques, which is also not went over in detail both in the lecture and the notes. So if you're interested, here is a supplementary material that I found online. And here is the Fréchet embedding. It's basically given a metric space and a list of subsets of the metric space. The embedding you compute is basically to find the distance between the new point you want to embed with all these subsets and define the distance between a point and a set as the minimum distance that you have with any elements of that set. So this is the Fréchet embedding. These two theorems, they are good to know, but also they don't really serve any purpose with respect to the rest of the material. So
hold on. What are the two theorems? The first theorem, I think I got it.
Yeah.
What is the second theorem?
Oh, sorry, it's not a theorem, it's a definition, sorry. Yeah.
So what is the relationship of the Fréchet embedding to that Broudoin? Did you say Broudoin?
The Bergens theorem.
Bergens theorem. What are their relationship? There is no relationship.
The relationship is that this definition is used in the proof of this theorem. Yeah, it's a definition that was constructed to prove this.
So what does it mean? I still don't understand what it means.
Yeah, so
let me give you my kind of understanding, my interpretation, just to converge to whatever it really means. So here is my understanding. So here somehow the Fréchet embedding we didn't really, or that embedded definition itself didn't specify how to choose S, right? But yeah. I assume that theorem somehow shows that there exists like log square n number of S sets, such that if you select those S sub I sets carefully, then that Fréchet embedding guarantees that Bergens theorem distortion limit. Is that how it is? Is it how it is done, or is different?
Actually, I didn't really go into detail of the proof this one, so I'm not sure. But again, I can provide more materials if we're interested. Proof, yeah.
No, I don't need to go into the details of the proof, but at least I want to understand what the proof means and exactly how we can use it. That's pretty much what I'm interested in. But right now, when I look at that Bergens theorem, it's an existence theorem, but somehow the way that you explain that is somehow there is a constructive part of that theorem that somehow help us to construct such an embedding. And I'm just trying to see whether Fréchet embedding is some kind of an embedding scheme that somehow makes that construction possible.
Yeah, I think that's true. That's why they use it in the proof. Yeah.
And Fréchet's embedding is actually a quite interesting. This is a very, very interesting construction of like embedding, because in some sense we find S like R anchors. And then simply by computing the distance from there, and then that is very good embedding. That's somehow what Fréchet embedding is somehow indicate if we believe whatever the earlier Bardouin's theorem, and that is exactly how they are constructed. So actually, there seems to be some very deep implications that the combination of these two seem to have. Simply measure, so like find k anchor points in our space, and then just my embedding will be the distance to each of these k anchor points. And that embedding is a very good representation of the metric structure of my overall data set. Seems to be very elegant and simple way of constructing an embedding.
Okay.
It'll be great if you can actually later tell us more about the connection between Fresher embedding and Baldwin or Bergens theorem.
Sure. Yeah, I will include that in the email. Yeah. Okay. All right. Thank you. So maybe let me continue.
Yes, please.
Yeah, sure. So now we go into the first part into actual algorithms. And we talk about embedding the Euclidean space. This is basically the part that I think we are familiar with. So it's a very good review material. Before I start, I just want to go over the notations. So assuming we have a data sets of endpoints, each vector with m dimensions, and we're given a Euclidean matrix of distances, which are square distances, and we can define a gram matrix, which is a matrix whose entries are the inner products between pairwise points. And we can establish this relationship between the distance matrix and the gram matrix. So this is basically the entry. This is what you obtain after you break down the inner product into after you break in the two norm into inner product notation. Basically, this is what you get. And this is the matrix notation for this one. So basically what this one transpose means is basically that given a vector of n dimensions, this is basically a vector of all the diagonal elements of the gram matrix. You basically repeat each element on the same row. So for example, if you have like G1 to Gn as a column, the first row would be all G1s and the second row would be all G2s. And this one is to replicate the row vector into a matrix. So this is just a matrix notation for this very expression. So now with a Euclidean setting, the inverse problem is that given distance matrix or gram matrix, how do we recover the data points? So one aspect of this point is that it's not really well-defined in its original form because a lot of transformations preserve pairwise distances. They're called the rigid transformations such as rotation, reflection, or those type of symmetries. So the mappings from X to G is not one-to-one. And in this problem setting, to simplify the problem, we care about case where data is centered, which is basically, if you sum up all the elements or the data points, you get 0. And this is this assumption is actually not arbitrary because you can achieve this by constant shift your data set, and it doesn't affect your pairwise distance. After centering, you can see that the gram matrix also is centered because this part is 0. And with the notation again, if I define this J matrix to be, which is called a centering matrix, this way I can write the gram matrix in this form from my distance matrix. So what we want to do is we find the embedding that preserves the Euclidean distance. And there are two approaches. The first approach is analytical approach. We can just use eigenvalues, eigendecomposition for the gram matrix. The reason why we can do this is because a gram matrix is a matrix of inner products. So it is symmetric and positive semi-definite. That means its eigenvectors are real and its eigenvalues are non-negative. So we can define the square root of the all its eigenvalues. That's why we can write the eigendecomposition this way. And we define our new embeddings to be this matrix. So the question I want to ask is, why can we use this one as our new embedding in case we want isometry? So the answer is quite simple. Just for interactive purpose, if anyone have idea, please just okay.
X transpose and X is an inner product between the various rows and columns of X, right?
Yes.
So now what it means is that we have represented the gram matrix, which is the inner product, as an inner product of certain kinds of representation. And as long as we make sure that the pairwise inner product is exactly the same, then these are exactly the same, like they preserve all the distances, because the distance between any pairs of the points are defined by the inner product. Because like if I take an inner product with this f, that is the length, and the inner product between these two is essentially the cosine, like how far away those are. So once we have those, then of course we have the entire distance, set of pair of distances. So now, because we found one representation of X, that is this decomposition, whose inner product is exactly the same as the gram matrix. Now we have everything.
All right, thank you. Yeah, that's a very detailed answer. Yeah, so yeah, we preserve the global structure of the gram matrix. Therefore, we preserve the pairwise distance. So it is a valid embedding. And if we don't want to have exact isometry and we want to perform tasks like dimensionality reduction, then we just pick the D. For example, if we want to have a D-dimensional embedding, we just pick the eigenvectors corresponding to the greatest eigenvalues, and it's very much like PCA. And as I will later show, under certain circumstances, PCA is actually equivalent to MDS. And approach 2 is more general. We don't really want to do isometry. Instead, we don't make any assumptions about the gram matrix. It can be from Euclidean. It could also be from geodesics or any other type of metrics. So in this case, we are faced with a general optimization problem in machine learning. So here I want to ask, given a sort of loss function that looks like a distortion or expansion or contraction, can we use a parameterized encoder as our embedding and then use gradient descent? So I'm just gonna say, so for example, here we can look at this loss function. We just say Z is our embedding, the kind of latent vectors we got from the encoder, and we can sort of minimize the sum of the square difference between the original data points and their embeddings. So given this objective, can we just plug and play using sort of an encoder to do the task? Yes, we can, of course. There's just a certain difficulties, of course, with this objective. The first one is that this one is non-convex because we have a non-squared norm in square bracket. So it's not not 2 norms squared, and it's like inside this sum, this square. So it's non-convex, and it's also not differentiable. But we can of course use a subgradient descent in general to approach problems like this. However, in classical settings, easier because gradient descent in general is they don't give you lots of great guarantees. So here another more approachable analytical algorithm called the algorithm is used. It's called the full name is called majorization minimization, which I will cover later on when we talk about a variant of this problem.
What if I change it from the just absolute distance to square? What happens?
Oh, you mean from here?
Right. So instead of taking the difference between the absolute values, we take the difference between squares of the absolute distances. Then it will be much cleaner, because now we don't have square root. And then does the problem become any easier then, or it doesn't?
So I think if you do that, then let me think. You mean like 2 norms squared here?
Yeah.
If we use 2 norms squared here, then indeed we have, so we have like a 2 norm to the fourth, and then it's probably, the problem with this is probably more about numeric issues. It looks like you have some gigantic values if you use 2 norms squared, I guess. But yeah, it's an interesting thought. I like, this is what I like when I look at the literatures. Basically, they just use a 2 norm or like a 1 norm without square. Yeah, but yeah, I cannot think about exactly why it's not 2 norm squared. But yeah.
Yeah, we can go ahead. Thank you.
All right, thank you. So here, just want to talk about the relationship between MDS and PCA. PCA is something that we are very familiar with. You can look at PCA from very multiple different perspectives. The easiest one is probably to find a linear subspace of your covariance matrix such that you have you can project your data onto it. So the PCA, basically you end up solving an eigen decomposition problem with the covariance matrix. With MDS, you're solving a problem with respect to the gram matrix. And this two looks very similar. And in fact, if you do a single value decomposition of your data matrix, you find that they end up sharing the same set of singular values or the eigenvalues matrix. So because the eigenvalues, they encode your the sort of geometric information in this case under the Euclidean 2 norm. These two algorithms give you the same results. And of course, we need to look at the dimensions. It's the gram matrix n by n and the covariance matrix n by m. So the number of non-zero eigenvalues in your end up being the minimum of these two. So just want to make this point even more clear, I actually want to show you some code demo for this topic. All right, so here I have some code loaded from the scikit-learn library. Basically, this is a data set that's well known in the manifold learning. It's called a Swiss roll data set. Looks like a Swiss roll in 3D. So the data point, there are 1,000 data points of 3 dimensions. So here I computed the covariance matrix, and here I compute the gram matrix. And I can apply the singular value decomposition, and we can take a look at the eigen value matrix. So if you use the covariance matrix, you end up with a 3 by 3 covariant eigenvalue matrix, and these are the 3 eigenvalues. And you can look at the other case where you use the gram matrix. Here you can see that we have these 3, and everything else is pretty much 0. The reason why they're not 0 is because of the numeric algorithms underneath, but they are pretty much non-significant compared to the first 3. And then in the so basically this is the Swiss roll. And if you use the scikit-learn library to compute PCA versus MDS, they actually look quite different, because it turns out the MDS MDS algorithms in scikit-learn is not exactly using SVD. It's using an iterative algorithm that's look like algorithm I'm going to cover later. However, in R, they use SVD. So you can see if I use the Swiss roll data set and I use PCA and MDS, they give exactly the same kind of embedding in 2 dimensions. That's the first and the second principal components, and here similar stuff. Yeah, so that's just want to show you that they're equivalent in this setting. Okay, so there's a more scalable version for the MDS algorithm, because you can see this is a global algorithm. We basically have n square storage because of the gigantic gram matrix and a pairwise distance matrix. So this is an attempt to make it an online algorithm. And you start with, instead of all the points, you select a subset of L points that serves as landmark points. And you compute the gram matrix and embedding using this subset. And later on, whenever you have a new points, you basically just extrapolate using this formula. So how is this formula obtained? We can see it. We can see it here. So here we see the embedding.
I need to go back. We need to go back.
Yeah.
So here, so picking a landmark points, that makes sense. So that part I understand. Up to there, I understand. So how do you use the landmark to construct either the distance matrix or the gram matrix?
So the gram matrix is just the pairwise inner product matrix of the landmark points, right?
Oh, I see. So it is not like we are computing the distance between landmarks and other points.
Yeah.
We just take a small sample, and then we create the distance matrix or the gram matrix just between the land or among the landmark points.
Yes,
that's what you're doing.
Yes.
Okay. And then could you go over the middle part, like exactly? And so now what do we do? And then what is the claim?
You mean this part?
Right, that part, yeah.
Yeah, this is exactly what I'm going to go over in the next slide.
The next slide, okay, good.
Yeah, so the next slide is about how this is derived. So again, to design an online algorithm, sometimes what you do is you write the entire thing in a recurrent formula, and you use this recurrent formula to extrapolate. And here exactly what they did.
Hold on. I don't understand what is X bar and what is P. Could you go over what is X bar and X bar?
Yes.
Yeah, thank you.
X bar is, if you remember from our earlier talk, it's basically the embedding matrix. It's basically your after MDS, your embedding. This is basically one part of the eigen decomposition of your sorry, it's probably here. Yeah, it's here. You see the X bar is our embedding matrix we obtain in the end, and the P is the pairwise distance matrix for the entire data set. That's P and X bar. Okay,
essentially X bar is the half of the gram matrix.
Yeah, it's the
square root of the gram matrix in some sense. Yeah.
So let me go back.
So the assumption then is that we start with the gram matrix based on the landmark, and then we get this X bar.
No, here we are just, I'm just trying to go over how that, so this is separate from landmark. This is about how we can use how this formula is designed. Basically, this is.
I see. So here you're not, so at least so far in slide 21, you are not assuming any landmarks yet.
Yes.
This is just based on the complete gram matrix.
Yes.
Okay.
Yes. Thank you for the clarification questions. Yeah. So here, remember this is what we have, and what we are trying to do is write it in this form. We try to write it in this kind of recurrent form, and we use this formula to extrapolate. That's what the design of the algorithm is.
I don't understand though. What do you mean by recurrent? What do you mean by recurrent?
So what I mean is basically this. X equals fx. You can write x into a function of itself.
Why? What are we trying? What is the intuition behind it? What are we trying to do there?
What we are trying to do is to basically making a batch algorithm into an online algorithm. And I think the idea behind how you do that is you take the whole batch and you write the whole batch as a function of itself. And then you try to extrapolate into an online version by using a subset, and then use this exact same formula for a new point to see.
Okay. So let me try to actually rephrase or explain what I think I understood from what you are saying. So here, the basic idea or eventual goal that you want to get to is we want to compute the correct X bar. That is our eventual goal, like the X bar that we are supposed to get from the gram matrix, right? But what you want to do is we want to avoid this singular value decomposition of this large gigantic gram matrix. So somehow I think the basic idea is that we start with some either random choice or some of our best guesses about the X bar. And then we want to identify some kind of a refinement function F, so that if I plug in the current estimate of X bar and then pass it through the refinement function, then I get a better estimation of the X bar. And then I just want to repeat it again and again so that it converges to a value. Is that what you're trying to do?
Yeah, I think that's what it is about. Yeah.
Okay, so now then our goal is to somehow come up with that recurrence relationship, some kind of an operator or function that works on the X bar and then gives us the next iterative version value of that X bar. And somehow your claim here, or whatever the author's claim or whoever the claim here is, somehow the equation on the right side in the middle is somehow representing that formula.
Yeah.
Okay, good. So could you explain that what it means then?
Sorry.
So I don't know. I don't get this formula. I have no intuition about this formula. So if you can explain the intuition behind this formula, maybe that'll be really helpful.
Okay. Let's see. So maybe let me go here. So let's see. What is PI? PI is given a new point. I want to find the distance between it and or the landmarks that I already found. So that's PI. And the G is the diagonal of the landmark. Basically, this is the gram matrix for the landmark points. So what is the diagonal of the
Hold on.
Yeah.
So G diagonal between X bar transpose and X. So here your assumption is that G is a gram matrix or between the landmarks.
Yeah.
And then what is piece of I?
Piece of I is the vector between, like, for example, if you have a new point xi you want to embed, you compute the distance between xi and all the landmark points, and you obtain a vector. That's pi.
Oh, okay. So here the distance is just absolute distance. It's not the square or anything like that. It's just the absolute distance between whatever new point for which you want to compute their embedding and the distance to the landmark, L landmarks in this case. Yeah.
In this case, it actually should be square distance, because that's how
the square distance.
Yeah.
Oh, okay. So square distance is good. Actually, I like square distance usually. So that is fine.
Okay.
So now that is PI. So in some sense, this one is kind of this one is actually related to that P matrix that we have been talking about earlier. The matrix of all the square distances between all pairs of the points, right?
Yeah.
Very related. Not exactly the same, but somehow very related. And then what? So that is PI. That is the definition of PI. So what is the next line then?
So this is, I think, the eigenvalue. The eigenvalue. Okay. Let me go here to see. Yeah, it's the eigenvalue matrix of your landmark gram matrix. So basically, that's after you perform an eigen decomposition of this matrix. This is the omega the lambda you got.
But it reads like in the lines above it, it says lambda using full MDS. Does it mean that it's not just based on the landmark?
No, the full MDS means it's basically just saying using MDS. So yeah, it's not on the full. It's only on the landmark.
Okay.
Yeah, it's on the landmark. Otherwise, it's pointless to use.
The dimensionality will not be the same.
Yeah.
So here the G is a vector, is it?
Yeah, G is here. Yeah.
G is a vector that consists of the diagonal entry of that gram matrix between the landmarks.
Right. So
if you actually do that, it's just these are just the absolute or the square length of the landmarks.
Right.
Yes. That's the That's the square to norm of each of the landmark vectors. Yeah.
Right. And then the way the claim here then is that once you do that, and we compute the square distance to the landmark for the new point that you want to embed. And if we take the difference between that pi and the square distance, and then pass it through x bar, and then pass it through the eigenvalue, inverse of eigenvalue, then this one is a good embedding. That's the claim. It seems. Is it?
Yeah.
Kind of makes sense because I think partly because I have done similar things many times before. So I cannot really explain why, but somehow this one probably will work out. That is my sense, but a little bit hard to see the rigorous kind of reasons of why this is really giving us a good embedding. And they claim this is an online algorithm because now we can compute just based on a few landmark distances, right?
Yeah.
And then here, X bar is not the X bar on the entire original data. These are just based on the landmarks, right?
Yes.
I'm talking about the third formula for xi bar is equal to that one. That one is also just for the landmarks, right?
Yeah, yeah.
Otherwise, the dimension will not check out.
Yes, that's the landmark.
Yeah. I have a question. Seems to me the landmark points should be very well selected, otherwise it's not that representative.
Right. That seems to be my kind of intuition too.
Yeah, but I think in the notes it's actually saying there you can use random sample.
Random sample. Yeah.
Yeah.
If you pick many random samples, maybe it'll be fine. Yeah, I guess it might be a trade-off between selecting a few very good landmarks or just take many random samples and then somehow it will work out.
Yeah, but yeah, I think it's kind of tricky with this kind of randomized algorithms. Yeah, I think there should be some proofs. I just didn't, it's not in the note and I didn't really look it up.
So here, what is when they say this is an online algorithm and it is good, what does it exactly mean? Good in what sense? So it is preserving the original matrix space or the metrics, or good in what sense?
I think it's mostly that you trade off isometry with space storage. I think
Minimizing
it's just
distortion.
Yeah, it's just a more efficient, but it doesn't give you exact isometry.
Yeah, it will not give us exact isometry, but I just want to get a little bit better sense of when they say it's good, exactly good in what sense? Is it more like providing some kind of a probabilistic epsilon guarantee when you have certain number of the landmarks, or is it more of like some maximum distortion is bounded by some number based on the number of landmarks we have? I'm not sure exactly what is the guarantee that this particular algorithm provides.
Okay, yeah, so this is another thing I'm going to write about maybe later because it's not in the material, so I need to look it up more.
Okay, thank you.
Yeah, all right, thank you. Okay, right, so this is another variant of the MDS, and this one is talking about the approach 2 we mentioned earlier. You're presented with an objective and you try to optimize it. So we want to find the embedding that minimizes this, and this so the notation here is D here is your original pairwise distance matrix, and Xi and Xj are actually embedding vectors. So in their lecture notes, they changed the notation this way. And here basically you decompose this term.
Why do we have 0 there? D sub 0?
It's not mentioned. I think it's just D, not D0. Yeah. Okay. Because we don't have a different version of the pairwise distance matrix. Yeah. But but this is basically just the pairwise distance matrix because you see it's only 0 here. There's no other like 1, 2, 3. So you decompose this into 3 terms. So this is the constant, and this is the sum of the pairwise distance. And you can write it in this way. So do you guys feel this is comfortable with this, or do you want me to derive this trace format?
What is J? Oh, J is right there. Okay.
Yeah. So clear, or do you want me to derive it?
I'm fine.
Okay.
I don't know about the other people. Will be fine.
Okay.
I have done something. The reason I'm fine is I have done something similar many times before. So I kind of, even though I don't really, I think if I think about it, I'm sure I can.
Okay, let me actually derive it. All right, so okay, so let me derive it. So can everyone see the screen? Yeah. Can you guys see it?
Yeah, I can see it. Thank you.
Sure. So what we have here is ij xi minus xj squared, right? So what is this exactly? This is actually Pij. It's the pairwise distance between 2 points, so it's Pij. And if you recall, I have some note here, so I need to bring it up. So if you recall the relationship we derived earlier, the Pij can be written into gram matrix Gi plus Gjj minus 2 Gij, right? That's what we have.
Yes, you needed to put that summation of ij before pj.
Right. So we can expand this one. So what's the first one? The first one is you're basically, because here you only have index for I, so what we end up is actually trace of gram matrix G, right? Because I is basically the diagonal times n. That's what we have for the first term. For the second term, we have a similar story because your gram matrix is a square and symmetric matrix. So again, we have n times trace of G. And the third one, it's actually the sum of all the elements of the matrix. And I think in their MIT's natural nodes notation, you can write it this way. So G is an n by n matrix. So we want a scalar. So what we end up having is this. It's 1 transpose 1. So 1, recall, is a vector of all ones. So this is a n by 1 vector, and this is 1 by n. So this is basically another way to write the sum of all the entries of your matrix. So once we have this, we can sort of combine the first 2 terms into trace of G times 2n identity. And we can, because this is scalar, we can basically apply trace to it. And that's 1 transpose G 1. And we can apply the cyclic property of trace. So what we end up having is, first one, we just write it as this, and the second one, we can put the G front. Yeah, and we can combine these two using 2mi plus I 1 transpose, right? So now we can just apply the, I think there's a definition for J. J is 1 minus m over 1 over n 1 1 transpose, and v equals 2n times this. And we can actually see that this term in the middle is exactly the V matrix. So we have trace of, and we can write the gram matrix as X transpose X. And again, using the cyclic property of trace, we end up with the form that we end up having, which is XV X transpose. So that's the derivation for this.
Don't we have a difference of the sign in terms of positive and negativity? No.
Sorry, you mean?
Could you show me your derivation again? Maybe I just. Oh, okay. So the second line should be negative. The last one, the third.
Oh, okay. So yeah, yeah. That's that. And I'm missing a 2. Yeah. So
No.
exactly. That's
Then
two.
everything's fine. Okay, good. Yeah.
Yeah. Yeah, and yeah. Let me just correct everything because this is all minus, and we have a 2 here, 2 here, and 2 here. Yeah. Sorry. Yeah, that's right. Okay, so yeah, that's the derivation for this part, and we break it up into these 3 parts, and now comes the optimization part. So the optimization algorithm in this case is called MM algorithm. What it does is basically you try to find an proxy objective, an upper bound for your objective, and then you minimize it. So if you look at this name, this is very similar to the EM algorithm that we saw before. The EM algorithm is basically used for the probabilistic models, and where you try to find the variation lower bound, and you basically iteratively maximize that lower bound.
I'm sorry, I lost my context while I was trying to follow the proof. Could you go back 2 slides and then explain to us what we were trying to do? What did you try to do?
Yeah, so what we're trying to do is to minimize this objective.
Minimize that objective.
Yes,
and then here d sub ij is a constant that is given to us from the data.
Yes.
And then what we can play with is xi's. The xi's are the embedding.
Yes.
And then somehow you want to change the xi's to minimize that, essentially the energy function.
Yes.
Difference. Yeah,
yes.
Stress. They call it stress. Okay. And then here, hold on. And then could you go over what are the significances of each of the conditions that are listed there after the 4th bullet point? Like sum of the d squared is the constant. What do they try to say there? It's of course constant because these are constant, but what does it mean?
This is basically just breaking it up so that you can have a clearer look at what kind of functions we're dealing with in this optimization problem. So it's a constant. That means we don't have to really care.
I see. So here what we did was that we expanded the f of x inside the summation. And then once you expand it, we have these 3 separate terms. The first term is d sub ij squared, and then that is a constant, so we don't have to worry about it. And the second one is, or the third one is square of the xi minus xj, which can be represented as the trace. And then the third term is -2 times d sub ij times the distance. And then that has that kind of a formulation.
Yeah.
Okay. And then from there, then what is the next? Like, how does it go from there to the next line?
You mean from the next page?
No. From the third line in the equation to the 4th line.
From here to here?
Yeah, from there to there. Like what is it? How do we go there?
So I think it's just it's similar to what we did here. You write the sum of the difference between the distance, pairwise distance between the 2 vectors into a trace format, and then you basically rewrite the whole thing into this way.
Okay, and then here, what is b sub ij?
So it's just it's basically you kind of define a function over x under these 3 conditions. I think it's just a way to write it in a simpler format. So in the end, what we care about is just a trace minus trace.
No, I understand. I think now I understand what we are trying to do. But here I'm asking about the definition of some of the terms that was not defined before. So here you're trying to somehow change the formulation in the third line into a much simpler or more beautiful, elegant formulation in the fourth line, which involves some kind of a trace. And then there you introduced a new matrix called B sub x or B of x. And B of x is defined to be three different cases. The first case makes sense because we know what D sub ij is and we know what xi is xj is. That is fine. The second possibility, 0 is fine, 0, no problem. Third possibility introduces some number, which is called B sub ij, which we never defined before. So I'm trying to ask you, what is that B sub ij there?
Oh, I see. B sub ij. All right, so I think we can just write it. We can just try to derive this thing ourselves. So then we can have a clear way of looking at it. So let me again try to derive this one. So so what we have here is this one. We have -2 ij xi not equals xj d, just dij over xi minus xj 2 norm times xi minus xj 2 norm square. So I think what we're trying to do here is basically we can let's see, ij xi not equals xj let's see, xi minus xj. This is what we have. I think actually this is we should write it into 2 ways, I think, because the result above is there's no constraint for xi not equals xj, so probably xij of dij minus xi equals xj in this case, right?
Yeah.
Oh, actually, no. If xi equals xj is not defined, well defined. So xi not equals to xj, it's actually an enforced constraint. Let me think.
Should we separate them into I equals j and I does not equal to j?
No, but if I equals j, that means this is 0, right?
Oh, okay.
So I don't really know why they consider I equals j, to be honest.
Yeah, maybe we can skip this one if you don't know. So here, let me actually briefly kind of remind myself about what we are trying to do. So what we are trying to do is we already given d sub ij as the input, and we want to minimize that kind of a stress or energy by somehow optimizing or adjusting the embeddings of individual xi's, right? So that is what you're trying to do.
Yeah.
Right? And then we have somehow, for now, let us assume that we have rewritten this the stress formula into the sum or difference of 2 traces. That's okay. Where we are then. Okay, good. Okay, so let's move on then, if you don't know it.
All right, let me also provide this in the email after. Yeah.
Yeah.
Okay, so then it becomes like now this is our objective after the rearranging and the rewriting. So this is, we define this function tau xc to be this, and now our objective is tau xx, because as we can see, first term xx and yeah, this is exactly the objective we had previous slide. So the first lemma is what's useful in this case is that, and all these two propositions are going to, the proofs are going to be shown in later slides. Here I just want to go over the basic idea first. So propositions 7.3 is basically saying that for an arbitrary z, we can use it as an upper bound for our objective, and they're only equal if and only if the z matrix is proportional to the x matrix. That's the first lemma. That means we have an upper bound. And now the second one is we want to minimize this upper bound. And also this is very important that this upper bound, it touches the objective. This is also a very important fact. So now we come to the minimization part. The second part is we want to minimize this upper bound. And that's the main idea of majorization minimization algorithm. So you basically compute the gradient of this function with respect to x, and then you update your the current iteration of your x to the next iteration. So it's an iterative algorithm like EM algorithm. And proposition 7.4 says that this optimization process is monotonic. That means if we follow this process, we will end up at some local, either local optimum or saddle point. Yeah, that's the two propositions. Any questions about the general flow before I go into the proofs for the two propositions?
For the first formula that we see there, why do we adjust x as opposed to xk? Because the proposition 7.3 is proof about when we adjust the second parameter of the tau, we can get to whatever the value. But here we are adjusting the first parameter of tau, which I really cannot make a clear justification.
So you're thinking that we should use argmin xk, right?
Or another way to think about it is that we have xk as the first term, and then we have x as the second term or second parameter, and then we optimize over x. That might be another way of doing it.
没有，他们不同步。
Sorry.
No. So I'm a little bit hesitant of just taking it at the face value because of the proposition is over the second parameter, and then the actual formula is over the first parameter. That is my hesitation.
Let's see. So if we look at this one, this original formula, only this term depends on z, right?
Right.
But we want to optimize with respect to both the first and the second term, right? So if we only use xk, then this term has no xk, right? This term has no xk. Xk is only here, z with z.
Right.
So objective should optimize with respect to the entire thing. So all this term and this term. So I think that's why we optimize using x, because we also care about this term. Otherwise, we would just have a constant here with respect to xk. So it's always 0.
I see. So in some sense here, we are trying to optimize the upper bound.
We are trying to minimize the upper bound. Yeah.
Yeah, we are trying to optimize the minimize the upper bound.
Right. Only the first constant term we don't care, but we care about both terms. And this term depends on x, not z. So I think that's why we do argmin x.
I see. Kind of.
Yeah. Okay. So yeah, the recipe is very similar to EM. We have a bound and we have a process that's monotonically decrease or increase it. So we end up having a local optimum. So let me now show the proof for proposition 7.3. So the proof for proposition 7.3 uses the Cauchy-Schwarz inequality. Here are these two lines are the inequality and the form that was used in the proof. So this is if we go back, this is the third term. This is a third term because z only depends on the third term. We just need to show that the third term is greater when we take arbitrary z compared to x. So by definition, we can convert the trace form back to this form, and we can kind of rewrite it in this way, and then we can sort of using the inequality to get this one. After rearranging, we get this form, and then we just convert it back to the trace format. So anything not clear about this process? Okay, so if no problem, then I go to the proposition 7.4, which is saying that this optimization process is a monotonic. And the argument is very standard for this type of iterative algorithms. The first one is basically f is basically tau xx. We just plug it in. And then the second one is by the proposition we just proved. Any arbitrary z that's not equal to x, it's upper bound. So this is why it holds. And then by 7.8, which is our second step, we are finding argmin. So by definition, it is less than or equal to this one. And then by definition of our objective, we basically rewrite it as fxk. So that's the whole process for proving proposition 7.4. Anything not clear about this one? Okay. Okay. Cool. So now we have these two, and that's all we talk about for this algorithm. We don't talk about other like convergence properties, like how good is the convergence, etc. We just prove these 2 points. And again, it's not covered in the materials. So I found something online. And if you are also curious about the convergence properties, I can provide more details later on.
Why is it called majorization and minimization algorithm? What is majorization and what do we mean? Minimize, we do minimize here, but why?
Yeah, so this is a very interesting nomenclature because I look online, majorization. So this is an algorithm that's mostly used in the biology community. So minimization and majorization actually they are used interchangeably. There's another process called minorization, maximization. It's like the same kind of nomenclature, but yeah, it's also my first time seeing this algorithm. So it's I'm not very sure why they name it this way.
Was it part of that MIT lecture, or was it a different material that you got from somewhere else?
So this is exactly the material in the MIT lecture. They didn't really talk about other things. Yeah.
So this is part of the lecture. Okay.
Yeah, this is part, but they didn't really talk. They didn't really expand into this algorithm.
Oh, I see. So the topic was mentioned, but they didn't go into this much of a detail.
Yeah. So these proofs, they come from the lecture notes, not from the slide.
Oh, okay. So, okay, good.
Yeah. Okay, so here I just want to give some examples about embedding.
So I have a question.
Yeah. Okay. Let me go back.
Why do we do this?
Oh, why do we?
Why do we do it? Like what? Can't we just like compare to, let's say, the landmark-based algorithm, right? So now once you have the landmark, we know how to embed everything else. So why can't we just do that? What's the benefit of this majorization and minimization?
I see. The biggest advantage for this one is it's very generic. Here we don't have a Euclidean assumption. You see, it's a generic optimization problem where we don't know if this D matrix is a Euclidean distance or geodesic distance. We just solve it using optimization. That's the major part about this Smakov framework. You don't have that Euclidean assumption. Yeah, the landmark MDS has Euclidean assumption, like the original MDS. MDS is confined to Euclidean space.
And compared to, let's say, if you compare to the case where we do the gradient descent, what's the benefit of doing this kind of very specific optimization?
Right, exactly. So that's why. So I think this is very similar to the idea of preferring algorithm like EM, like compared to gradient descent. Is that gradient descent is like it's like a generic algorithm that you can just plug and play. But in lots of cases, for example, here it's again it's non-differentiable, so you end up using subgradient descent. And I think subgradient descent is like for each non-differentiable point, you have multiple subgradients, and you randomly pick one subgradient. But it's very likely that your subgradient is not going to the descent direction. However, from here, you have that monotonic guarantee, similar in EM. Basically, once you find that variational lower bound, every step you go through is increasing that lower bound. And here, every step you go through is decreasing that upper bound. So you have this kind of, I guess, kind of convex behavior for the second step. But with gradient descent, you really don't have any guarantee for convexity at your steps. So you basically just hope that your optimization works. But here you have, I guess, a easier framework and one that has better theoretical guarantees.
Could you go to slide number 23?
Yeah.
So then, what are the exact kind of a computation we need to do here? So B sub x, I'm looking at the second kind of a iteration step. The first iteration step is not really, it's just a high level intuition of what we are trying to do. But in terms of the actual computation and algorithm, I assume we just simply plug in the formula that we given in the next, next equation, right?
Yes.
That's what we do. So now I'm trying to understand that next equation a little bit better.
This one?
Yeah, that one. So then it's what it really involves is really nothing more than a few matrix multiplication, actually, as long as we know how to compute the B of x.
Yeah, it's a closed form update formula. Yeah.
Right. So
we
we
can
just
compute a gradient. Yeah.
Keep computing that number repeatedly, and then we convert this to a number.
Yes. And as I mentioned before, it's very important that this upper bound touches the objective. That's so that when it converges, you end up updating the objective because it touches the objective, much like the EM algorithm. Yeah.
Right. So as long as computing B of x is reasonably efficient, which is, I think, is the case, except I don't know what the B sub ij is in the formula, but most other cases, those are all just diagonal lines. So those actually do not matter too much, actually, in terms of the overall computation. Somehow ultimately we know what it is. Others are simply renormalizing the x vectors and multiplying with the d sub ij. So that one will be straightforward. Is it? Very interesting. Okay, yeah, thank you. I got it. Thank you.
All right, thank you. I think it's very interesting for me too. Like when I look at it, also was thinking about gradient descent, but I had a similar kind of questions when I approach EM. But EM was very peculiar, where you have a latent variable structure, but here we don't. So I was really interested in. Yeah, I'll also provide more materials.
It somehow reminds me of kind of projection as well, like manifold-based kind of a optimization that we talked about last week. Because if you actually look at the formula of computing B sub x, like one slide before, maybe 2 slides before, or 1 slide before. Yeah, this one.
Oh, this one?
The next one is the next one. Here, what we do
this one?
is that one, B sub ij. What we do is we actually normalize based on their absolute, the height, the norm, right? The first one.
This, you mean this one?
That one, yeah. So we multiply that with the current xk in the next formula. So here that division is really normalizing into the sphere. And then we kind of multiply that matrix. So somehow it gives me similar kinds of sense of this is a projection onto the sphere.
Hmm.
And then somehow do some multiplication.
I see. Okay, there's a chat. Let me see. Okay. Yeah. Okay. Or interesting. So should I go on or?
Yeah, please go ahead. I'm just
Okay.
just noticed something interesting.
Okay, thank you. All right, so here is just an example about using the algorithm Markov we just talked about. We don't have any assumptions about the distance matrix are given. So if you even use the shortest path distance matrix for a graph, you can use this algorithm to find embeddings that somehow preserves the shortest path distance structure and with a different topology for the graph. So this is like an example. Yeah, and here is another example of using the geodesic distance matrix and using the Markov algorithm, which end up, if you change the distance matrix and you map it back to the original space, you end up having different geometric shapes. So these two examples just illustrate that the Markov algorithm doesn't have Euclidean assumption. It's a generic optimization scheme. All right. So now we have a little bit of time to go into the manifold chart. So there are a couple algorithms that's specifically dealing with manifold. So the first one is the manifold hypothesis, which is saying that the high dimensional data lies near lower dimensional, lies in the vicinity of a low dimensional manifold. That's why we have this kind of dimensionality reduction algorithms that's so popular. So basically, now this is a hypothesis that's just a sort of laid out without any proof or theoretical justifications, but it seems to be a very useful heuristic. And here I want to give some examples. So first, we need to distinguish between extrinsic embedding and the intrinsic embedding. The extrinsic embedding is the Euclidean one that we just went over. Basically, all the distances are equally important because in Euclidean space, you don't have any preference for the geometry. But if you have actually a manifold as the embedding space, then it is better to preserve the geodesics or the intrinsic embedding of that manifold. And here, it's just two examples that shows here, it seems to be that the distance on the surface is more important than this one. So before, here again, I think like one of the MIT lectures is just that they just throw out some theorems without giving you lots of context. So here again are two theorems they just mentioned about that's well known in mathematics about embedding manifolds. So the first one is called the Whitney embedding theorem. It's saying that any smooth real k-dimensional manifold maps smoothly into R22K. Yeah, so I don't really have any visualization or anything or any proofs really. It's just stated. And the second one is the Nash embedding theorem. Any k-dimensional Riemannian manifold that meets isometric differentiable embedding. So it's basically built up upon this one. This one says it's smooth. And this one says if you have Riemannian manifold, then you can have a embedding that's isometric and differentiable. Yeah, so if anyone knows more about these two theorems, could you like maybe provide more context?
No, it's not. I don't know about this theorem, but this seems to be very, very fundamental and one of the most kind of the key things that we want to figure out. You know, so far our discussions have been mainly about that our original data already came from some kind of a Euclidean space, right? R to the K. And then somehow our data is within a subspace or some kind of manifold that is embedded in R to the n. From there, we wanted to do all these nice fancy things. But what this is trying to say is that let's assume that we have a manifold and we have no idea whether it's somehow embedded in the Euclidean space at all. All we know is that it's a Riemannian manifold that has a mapping from k-dimensional R to the k to this local neighborhood within that manifold that also admits some kind of a metric structure in the local neighborhood. So this one we have no idea that this can be embedded into some Euclidean space, right? And what this theorem says that this is always possible, right? And
Yeah.
so without this, we are not able to do anything really. Because of this theorem, now we can say that, oh, so given any kinds of arbitrary Riemannian manifold, let us assume that it is some manifold that is embedded in some Euclidean space, because this theorem guarantees that that is always possible.
Oh, okay. So it's basically the theoretical foundation for everything.
Right, for everything that so in all our real work, when computational work that we do, we always have to assume that, you know, we want to represent it as some kind of n-dimensional vector or 2k dimensional vector.
Yeah.
And then this theorem guarantees that that is possible, right?
Oh, I see. All right, thank you. Again, if you are interested, I can maybe provide more materials afterwards for this one. So here, I just want to give some examples of high dimensional data lying in a lower dimensional manifold. Here is a famous teapot dataset where you can sort of embed into like R2 into like a circle that with some distortions because of the noises in the dataset. Basically like that kind of encodes the rotational information in this teapot dataset. And another example is the well-known MNIST datasets, where this one is about how you write the digit 2, and you have sort of 2 degrees of freedom in their terminology of writing the top loop and the bottom loop. You can see that if you write the bottom loop as a circle and top loop as a circle, they end up like in this kind of place, and you have like a different. So I think this is basically the foundation for clustering algorithms. You like if you have this kind of a continuous smooth process, somehow they lie into this lower dimensional space, and you can visualize them using clusters. And the similar goes for hand gestures with a sort of 2 intrinsic degrees of freedom, as what they call finger extension and the wrist rotation. I remember that earlier, perhaps in the paper reading, I couldn't attend, but I know there were like some discussion regarding protein folding, and I saw some text about something called the intrinsic degree of freedom for protein, but there's no like information given for the materials. So something extra I think interesting regarding this. Yeah. So the key of learning the manifold is again to approximate using tangent space, because we don't really have the computational capacity to have these smooth infinitesimal structures. We sort of care about the local structures, and you can see here we have sort of like a Gaussian kernel or Gaussian disk for each of these surface, and this is exactly one of the approaches that's used in manifold learning, kernel-based method that we're going to cover. So yeah, I think we kind of run out of time now. Should I like maybe continue next time?
I think so, because you have half of the slides left, right?
Yeah.
Okay, sounds good.
All right, thank you. Thank you, Professor Cho, for the questions. I'm going to write some
I hope
emails.
you don't take my questions in the wrong way. I just want to learn, you know, and I need to know.
Yeah. Yeah, I also want to learn. I mean, sometimes it's good to go into the rabbit hole. Just the math rabbit hole is especially a dense one. So yeah, I'll try my best to provide the materials. Yeah.
Thank you.
All right, thank you.
Thank you. See you next time.
Bye.
Thank you. Bye.